All right, a very good evening, everyone. So, we are into the 10th lecture of social media analytics. And let us start with our today's lecture. I hope my screen is visible and I'm audible to everyone. All right, I'll also mute your mics. Okay, so let's quickly start with a recap of what we have done in our previous lecture. So in our last lecture, we started our discussion with link predictions. Okay, so given a structure of network, given a network, so how can you predict missing links? Okay, so in link predictions, we have basically studied two types of problems. So the first problem was that given a static network, how will you identify the missing links in this network? Okay. And the second problem was that given a dynamic graph, how can you predict that like after some time, like when the time evolves? So after some times, which will be the new links that will be there in your original network? Okay. So we have seen that link prediction can be divided into these two types of problems. One was on static network and other was on dynamic networks. Okay, so after that, we have also seen that a link prediction problem has a lot of applications. Okay, so starting from the recommendation of friends, then a recommendation of products. Then we have also seen that like for the reconstruction of the networks. So the link predictions have a lot of application in all sorts of areas. Okay, and then we saw that link prediction can be solved by using these different type of algorithms. So we started with heuristic models. Okay, so heuristic models, they are further divided into two types. The first one is local measures. So in last lecture, mostly we saw these local measures. Okay, so how based on your neighbors you can predict the links. Okay, how based on the number of common neighbors or based on the neighbor's property one can predict the links in the network. Okay, and then like in today's lecture we will be initially focusing on global methods. So what are the global heuristic methods based on which you can identify the links in the network? Then there is another category that is probabilistic models. In today's lecture, we will also be seeing the algorithms based on probabilistic models. Okay, so yeah, so in the local methods, we have covered that we can identify the links. We can predict the links based on your common neighborhood. Okay, so more the number of common neighbors between two nodes, more is the probability that these two nodes will be connected. Okay, then we have seen that this common neighborhood notion can be normalized, and that notion is called as Jagged Similarity Index. Okay, so we have also seen that how we can use preferential attachment or the degree of the nodes in order to identify or in order to predict the links. Okay, and then there were some other algorithms as well that we have covered in our last lecture. Okay, so this is going to be the agenda for today's lecture. So until now, I have given you a quick recap of what all we have covered in our last lecture. So in today's class, firstly, we are going to see the global methods. Okay, and I will also be telling you what is the difference between global method and the local heuristic methods, in which situation you should choose which of these two. Okay, and then we have probabilistic methods, and then we have information diffusion. Okay, so like after the probabilistic methods, we will be done with our topic link prediction. Okay, and then we will be moving on to our next topic, that is information diffusion. So given an information, how this information spreads in a network. Okay, so in this topic, we will basically be studying the algorithms around that. Okay. So what is global heuristic based link prediction? Okay, so we have already seen the local heuristic based methods in our last class. So now the question is, what is global heuristic based method? And like, why do we need a global heuristic method at first? So anybody, can you think of a disadvantage of the local method? So what could be the disadvantage of the local heuristic method? All right. So you have seen that, okay, suppose I have these two nodes and I want to predict that whether there is link between these two nodes or not. So now in local methods, mostly like we try to see that how many common neighbors are there. Okay. And then based on the number of common neighbors, we try to identify the link. Okay. If more the number of common neighbors, more is the probability that there will be link between these two nodes. Now, if you see in this particular algorithm, in this particular notion of local heuristics, we are only considering the neighbors. Okay, so we are not considering the entire network. So the entire network might have a different impact on these two nodes. Okay, so in these set of algorithms that we have covered in our last lecture, we are considering only the local neighborhood. Okay, so this is more like a greedy algorithm. We are only seeing the local neighborhood. We are not seeing what is the impact of the entire network on this. So that's why we need to move on to the global heuristic methods. Global heuristic methods are like more trustable. Okay, so because in this global method, you are considering the entire network and then you are trying to identify some score. So because you are considering the entire network, so these methods are more trustworthy. The results of these methods are more trustworthy. Okay, so now let's go through this slide and let's try to understand what is a global heuristic method. So basically, this slide will give you an overview of the global heuristic methods. The global heuristic method is a link prediction that predicts missing or future links by using the entire structure of network. Okay, so first point is that in global methods, what we are going to do, we are going to consider the entire network, and that entire network is going to contribute towards the score. Okay, so it assigns a score to every pair of nodes. So as we have done in our last class, what we have done, we have considered all the pair of nodes, and then we try to assign those pair of nodes some scores that were based on local heuristic. So same as the notion here. So we are going to consider all the pair of nodes, and then for all those pair of nodes, we are going to assign a score, and then that score is based on the global heuristic. Okay, it assigns a score to every pair of node. Higher the score, higher is the likelihood of a link. Okay, so up till now, the idea of global and local is same. What is the difference? In the local method, what we have considered the local neighborhood. But on the other hand, in global methods, you use paths, walks, matrix operation to calculate the scores. Okay, so basically, when you will see the algorithms in global method, you will be seeing that we are mostly considering the paths in the network. Okay, so yeah, so in the next few slides, you will be seeing that how we are using these paths, how we are using the matrix operations in order to calculate the global measures. Okay, so now the first algorithm that we are going to see here is the CATS score. Okay, so now let us discuss what is CATS score. CART score is a link prediction measure used in the network. It measures how likely nodes could be connected. Okay, so now in order to calculate a link, in order to predict a link between two nodes, what it is going to see, it is going to see all the possible paths between these two nodes. Okay, so suppose I had this network. So suppose I had this network. Okay, and now I want to predict that whether node A and node B are connected or not. Okay, so I want to predict this link. So what I will do, I will consider all the paths through which I can reach A and B. Okay, so see, in this network, we have different paths. Like I have this path. Okay, let me change the color of my pen. Okay, so one of the path is this. Another path is this. Okay, third path is this. So there can be multiple paths. Okay, in order to reach from A to B, there can be multiple paths. So in this particular algorithm, we are going to consider all those paths. Okay, and then after considering all those paths, now what we are going to do, we are going see, the notion behind card score is that more the number of shorter paths, okay, more the number of shorter paths like this one, okay, like this one. So if I have more such paths, maybe let us assume that there was another node here. So if there were more, the number of shorter paths between two nodes, more will be the score and more is the probability that these two nodes can be connected. Okay, so yeah, so now we want to, give more preference to the shortest paths as compared to the longer paths. But however, we are going to consider all the paths. Okay, so the first point is we are going to consider all the paths. And then second point is that we are going to give more preference to the shorter paths as compared to the longer paths. So yeah, so if that notion is clear, so now let me explain you the formula for CART score. Okay, so this is the CART score. So firstly, let me consider just this part. Okay, so we are considering just this part of the formula. So yeah, so what it is calculating the number of paths of length p. Okay, so in this particular algorithm, what we are going to do, so first we will consider that, okay, I have this pair of nodes that is x and y. Okay, and then like I'll calculate that how many number of paths are there of length 1, 2, 3, 4, and 5. So let us suppose that 5 is the maximum length in the network. Okay, so I'm going to consider that how many paths are there to reach from x to y of length 1. This is length of length 1, 2, 3, 4, and 5. So now let us suppose that there are two paths of length 1, then there is one path of length 2, then there are maybe two paths of length 3, three paths of length 4, and one path of length 5. Okay, so now once we have this, we are also like I have explained you in the last slide that we are going to give more weight or we are going to give more priority to the shorter paths. Okay, so so let us suppose the value of alpha is 0.5. Okay, so what is alpha? Alpha is a damping factor that reduces the impact of longer paths. Okay, so alpha is a factor that will reduce the impact of longer paths. So how we are going to calculate the CART score for this data? So it will be, so firstly, we are considering all the paths of length 1. Okay, so there are two paths of length 1, and suppose alpha's value was 0.5 to the power 1. Okay, then we'll summation it with, now how many paths are there of length 2? There's one path. Okay, and what is the value of alpha? Alpha raised to power 2. Okay, plus now we have two parts of length 3, and this is alpha raised to power 3. Plus we have three parts of length 4 and alpha raised to power 4. Then we have one path of length 5, and this is alpha raised to power 5. Okay, so now in this formula, you can see that more the length of the path, so we are reducing its impact by using this alpha factor. So here the value of alpha is 5, 0.5, here it is 0.25, here it is 0.125. So you can see that the impact of the number of paths of greater length is being reduced by using the damping factor. Okay, so this is the formula for the CAT score, and using this formula, you can calculate a score that will tell you, so you can do this entire summation and this will give you a score. Okay, so now for each and every edge, so for each and every edge or for each and every pair of nodes, okay, so for each and every pair of nodes, you are going to calculate this score, and then you are going to sort those scores, and then you are going to consider the top few scores. Okay, so this was what we have done in our local heuristic method as well. So yeah, so these are the steps of card's centrality. First, you will compute the card score. So I hope the calculation of card score is clear to everyone. Is there any doubt? Is there any doubt anyone wants to ask? Okay, so I assume the calculation of card score is clear to everyone. Okay, so for each pair of non-connected nodes, okay, so this is important here. Okay, so you need not consider those pairs where you already have an edge. Because why? Because this algorithm is for predicting a new edge, right? So you are only going to consider all the pair of nodes that are not connected. Okay, so once you have all those pairs, you are going to calculate the CART score. Okay, then rank the pairs by the score from highest to lowest. Okay, so once you have this ranking, you can predict the links. Either you can choose top k pairs. Okay, so maybe like the value of k is 3. Okay, so for top 3 pair of nodes, you will say that there will be a link between these three pair of nodes. Okay, or in the other word, otherwise what you can do is you can have a threshold, and you can say that wherever the threshold value is more than so and so, there will be an edge. Okay, so this is how we predict the edges using the CAT score. So is it clear to everyone? Any doubt? Okay, so this was the first method. Now we move on to our next global heuristic method, that is called as hitting time. Okay, so what is the notion behind hitting time? So basically in hitting time, it is based on a random walk. Anyone remembers what is random walk? So we have covered this before our midsense. So anyone remember while calculating the page rank algorithms? So anyone remember what was a random walk? Class, please try to answer. It's okay if you're answering wrong, but please try to answer. What is a random walk in the network? Okay, so let me quickly revise what is random walk. So here I'll take an example of city Chandigarh. Okay, so you know that Chandigarh is divided into sectors. Okay, so the layout of city is in the form of square, and the entire city is divided into sectors. Okay, so for example, this is a sector number maybe 10, and this is sector 17. Okay, and this is maybe sector 34. Okay, so I have numbered the sectors. So sector 17 and sector 34 are the most popular sectors in Chandigarh. So now, you are new to the city, okay, and I give you a car. Now I ask you that you should go from sector 34 to sector 17, and these are the roads, okay. So these are the roads, okay. So you start from sector 34, maybe from this position. Okay, you start from maybe this position, and now you start taking a random walk. Okay, so at each junction you decide that whether you want to go to left direction or right direction or forward or backward. Okay, so at each junction you decide this. So maybe at this junction I decide to go in forward direction. Then in this at this junction I decided that I will go in the left direction. Okay, this at this junction again I have to decide, okay, so where I want to go. So maybe I decide to go in the forward direction. Okay, so now at this junction again I'll decide to go in some direction. Then here also I decide to go in some direction, and then here again maybe I decide to go in left direction. So this is a random walk. Okay, so randomly you are trying to reach from one point to another, and after certain iterations, you reach sector 70. Okay, so after certain, after some time, you will reach your destination, that is sector number 17. So this is an example of random walk. Okay, so is it clear what is random walk? Okay, so now this particular algorithm, it is based on a random walks or random shuffle. So in this, we start from a node X, okay, and then we move to the neighbors of X and X chosen uniformly at random, okay. So in this, what we will do, we will start from a node X. Now suppose node X has few neighbors. Okay, so because node X has few neighbors, now from these three neighbors, I will uniformly at random select one of the edge. Okay, so I'll select one of the edge, maybe this edge. Okay, so from here again, I have few neighbors. From all these neighbors, I will select one of the edge. So this process will be continued till I reach node Y. Okay, so you'll start from node X. You'll move to a neighbor of X chosen uniformly at random, and you'll repeat the steps. You'll keep on repeating the steps until you reach A, as we have done in this particular example. Okay, so now once you have done this, you will calculate the expected number of steps it takes for a random suffer starting from X to reach Y. Okay, so now like in this particular algorithm, I have explained you what is random walk. Okay, so I hope random walk is clear to everyone. Okay, so you know what is random walk. Okay, you start a random walk. Now, uh, like you suppose you start from X and you reach Y. Okay, and the total distance between X and Y was, let us suppose, 10. Okay, so now you'll keep on repeating this experiment maybe 10 times. Okay, so I repeated this experiment again and again 10 times, and for each time I calculated the length of this path. Okay, the length of the path to reach from X to Y. Okay, so now after 10 experiments, I will calculate the expected number. Okay, so I'll calculate the expected number of these 10 experiments. Okay, so that will be my hitting time for X and Y. Okay, so this score will be the hitting time for X and Y. Okay, so now there is this minus sign. You can see that there is this minus sign in this formula. Anyone can guess why there is a minus sign in this formula of hitting score? So please try. to answer this question. Why there is this minus sign here? Anyone wants to try? Okay. So, see, so if my expected number of steps to reach from X to Y is less, okay, so that means there is more probability that there will be an edge between X and Y. Okay, so lesser the value of HT, lesser the value of HT, more is the probability that there will be an edge between node X and Y. Okay, so if the average path length while doing random walk from X to Y is less, then the probability that there will be an edge between X and Y is more. Okay. And on the other hand, if this value is huge, okay, so suppose that if you are taking random walks and the average path length, okay, or the expected number of steps to reach from X and Y is maybe 100. Okay, it's a huge value. Okay, so if it is a huge value, then the probability that there is an edge between X and Y reduces. Okay, so that is why we have the negative sign. More the value, more the HT value, lesser is the probability. Lesser the value, more is the probability. So in order to, normalize this situation, we have this negative sign. Okay, smaller the hitting time between two nodes, closer is the proximity. So if like the two nodes have smaller hitting time, that means closer is the proximity of the node. Therefore, higher are the chance of their interaction in future. Okay, so yeah, so this is your hitting score. We can also have a normalized hitting score. Okay, so you will have some hitting score and you can normalize that value. How do you normalize that value? You can normalize that value by using the centrality value. Okay, so which centrality value? So which was the centrality value that was based on which was the centrality value that was based on random walks? Anyone remembers? Which was the centrality value that was dependent on the random walks? We have covered a degree as a centrality value, then closeness, betweenness, and eigencentrality. Class, please answer this question. Which one do you think is based on the random walk? Which centrality?
Betweenness.
Okay, so the correct answer is eigencentrality. So eigencentrality is based on your random box. Actually, in betweenness, we do consider the paths, but those were the shortest paths. Okay, so we considered the shortest paths between the pair of nodes. So that's why that was not a random walk. So yeah, so we will multiply the value. Okay, so suppose I'm calculating the hitting score between X and Y. Okay, so the hitting score will be some value. So we will take minus of that value, negative of that value into the eigencentrality or the page rank centrality of node Y. Okay, so we will, and the page rank centrality, if you remember, its value ranges between 0 to 1. Okay, so we will multiply that value here and the value will be normalized. Okay, so I hope this algorithm is clear to everyone. Hitting time algorithm. Okay, so now we are going to move on to our next algorithm, that is commute time. Okay, so just a second. So yeah, so the notion of commute time is very similar to hitting time that we have just now covered. Okay, so what you do in this, you start from node X, okay, and then randomly you try to reach Y, okay, as we have done in our previous algorithm, and you calculate the length. Okay, so you calculate the length here. Now you also travel back from Y to X. Okay, so here you are going to calculate two hitting score. One was from X to Y, and then the other is from Y to X. Okay, so once you calculate these two scores, so using the summation of these two scores, you can calculate the commute time score. Okay, and you can also normalize it as we have done in our last explanation. So you can normalize it by multiplying it with page rank centrality. Yeah. So these are all the global heuristic methods that we are going to cover. Okay, so with this method, we are done with our global methods. So now let's try to understand what is the difference between local method and the global heuristic method. So local methods are fast, they are simple. Why? Because you're only considering the neighborhood. Okay, so in this particular case, you're only considering the neighborhood of the particular nodes, but it is limited. While the global methods are more powerful, more accurate, but they are computationally costly. Okay, so these methods, they see, you have seen that here you need to calculate the paths, and path calculation operation is an expensive operation. Okay, so the if like I take an overview, so local methods are based on the neighborhood, whereas global methods are based on the paths. Okay, it consider the paths, and path calculation is always a more expensive operation, computationally expensive operation as compared to if you're calculating the degree of your neighbors or you're calculating some other heuristics of the neighbors. Okay, so local methods will be fast. So whenever like you need to apply these methods to very large networks, then maybe you can use local methods. But when your network size is moderate to small, so you can use the global method. So although they are computationally costly, but they are more accurate. And these are the different differences between these two. They consider the local method, consider the neighborhood, and the global method, they consider the entire network. Then here we have short hops. Why short hops? Because we are considering the neighbors. And here we have all the paths. Then accuracy, these the global methods are more accurate. We have already discussed. Computational cost, global methods have high computational cost. Then scalability. Scalability, local methods are more scalable as compared to the global methods. Because in very large networks, it's very difficult to calculate the paths, the number of paths between two nodes. So you know that path calculation is a matrix multiplication operation. So you need to multiply the matrix, and it is computationally very heavy. Okay, so yeah, so with that, we have completed the local heuristic methods and the global heuristic methods for link prediction. So now next we move on to our next method, that is probabilistic link method. Okay, so probabilistic link prediction method. So this method is based on the probability of existence of an edge. Okay, so for each non-connected edge, we are going to calculate a probability. Okay, so somehow we will calculate the probability that whether this edge will be there or not. So based on that probability, so again, like as we have seen before, what do? We generally identify a score, then we rank that score from highest to the lowest value, and then maybe we consider top k links for as the predicted links. Okay, so similarly in this case you are going to calculate the probabilities, then you can sort the probabilities from higher to lower values, and then maybe you can take the top k pair of nodes as the predicted edges. Okay, so the output of these algorithm is the probability that there will be link between the two nodes. Okay, so now we can take a break of 10 minutes, and after the break, I will be explaining this method to you. Okay. So before going to the break, we have started our discussion with the probabilistic model of. Okay. So we have started our discussion with the probabilistic model of predicting a link between nodes. Okay, so now, first of all, the probabilistic model, it is based on hierarchical networks. Okay, so we have already discussed different types of network, and one of the most common structure in the social network that exists is the hierarchical network. Okay, so like in your social networks in the real life, there are actually some kind of groupings. Okay, so for example, like if we see our family tree or if we consider all our relatives in our family, okay, so there is initially there are certain small groups, for example, families. These families are further connected into, bigger groups. So you can see that there is a kind of hierarchy in our social networks. Okay, so another example is, for example, in a college, we have different classes. Okay, so these different classes or these different sections can be divided into branches. Okay, so then branches can further be divided into departments. Okay, and then department can be divided into college. Okay, so there can be different colleges and so on. Okay, so yeah, so the nodes, they will exhibit this hierarchical clustering, or this notion of hierarchy in the network will be there in our real world social networks. Okay, and the probabilistic models, they are based on these hierarchical networks. Okay, so yeah, so the first assumption is that there is certain hierarchy in the network, and we are going to predict that hierarchy. Okay, so yeah, so let's first cover what is there in this slide. Okay, so a network is said to be a hierarchical network. So what is the definition of hierarchical network? If the vertices can be divided into groups. Okay, so there will be vertices or there will be nodes. Those nodes can be divided into groups, which can be further subdivided into groups and so on. Okay, and each group is formed in a logical order corresponding to a granularity or social unit. Okay, so each group will have certain meaning. Okay, so this is the definition of hierarchical network and can easily be rendered using dendrograms. Okay, so I would suggest that you should look into agglomerative algorithms. Okay, so there are these algorithms called as agglomerative algorithm. They help you to identify hierarchical clustering. So you might have also studied these agglomerative clustering algorithms before. And in the agglomerative clustering algorithms, you have something called as dendrograms. Okay, so dendrogram is nothing but a visual representation of the hierarchy. Okay, so the hierarchy will generally be in the form of tree. Okay, so as we have seen in this example, we have college, then we have department, then department is further divided into branches, and branches is further divided into sections, and so on. Okay, so yeah, so this the social network or this hierarchy is in the form of trees. Okay, and these trees can be represented in the form of dendrograms. So dendrogram is nothing but a visual representation of the hierarchy in the network. Now we will see what are the dendrograms. Okay, so but before going there, we should study that why are we studying the dendrograms? Why using the dendrogram is important. Okay, so let me explain you. Okay, so given a network, what we can do, we can unfold the hierarchy in the network. Okay, given a network, we can unfold the hierarchy in the network. We can identify or we can predict this hierarchy based on which this network was formed. Okay, so you will be given some network and you can identify this hierarchy in the network. Now, this hierarchy can be represented by using the dendrograms. Okay, this hierarchy can be represented by using dendrograms. And dendrograms, they explain this hierarchy. Okay, they explain that how this hierarchy is formed. Now, using these dendrograms, one can predict the probability that whether the nodes will be connected. Okay, so maybe you can see this in this form that dendrograms will give you certain communities. Okay, and based on those communities or based on the dendrogram, you can identify, you will identify the probability that whether the nodes are connected or not. Okay, so you know that the output of probabilistic algorithm is that you will identify the probability of the unconnected connections. Okay, so you will identify, like we used to calculate the scores in our global method and in our local method. So here we are going to calculate the probabilities. Okay, so the output is probability. So what you are going to do, what is a high level explanation of probabilistic algorithm? So you have this network, you will try to identify what is the hierarchy in that. Okay, that hierarchy can be represented by using the dendrograms. Okay, so once you have these dendrograms, you can predict the probability. So in the next few slides, we will be discussing how the probability can be calculated. And this calculation is very important for even for your like exam point of view. Okay, so now let me show you what are the dendrograms. Okay, so given this was the network, okay, so suppose this was the network, so you can construct these type of dendrograms. Okay, so this is your dendrogram number one, and this is your dendrogram number two. So for a given network, you can have many different type of dendrograms. Okay, so you can construct all of those dendrograms. And in the next few slides, we are going to see that we have a quantitative measure as likelihood. Okay, so we have this quantitative measure. So using that quantitative measure, you can identify that which dendrogram is more correct and which dendrogram is less likely to happen. Okay, so yeah, so and using that score again, you can you can identify the top five dendrograms, and based on those top five dendrograms, we can do our further calculation. Okay, so for now, you can keep this this explanation aside and try to focus on these dendrograms. Okay, so yeah, so you can see that this was a network, and let us focus that how dendrogram one is constructed. So here we, initially assume that A, B, and EF, these were the two edges that initially formed. Okay, so this can be based on the edge weights. This can be based on some node properties or some other heuristics. Okay, so yeah, so you have that A and B connect first and E and F connect first. Then A and B, they are connected to C at level 2. Okay, so this group is connected to C. Okay, and then this group is connected to D at third level. Okay, and then at fourth level, this E and F are connected to D. Okay, so this is the hierarchy in the network. Okay, so if you see here, like if I cut this dendrogram from here, you can see that there are three groups. One is ABC, other is D, and third one is EF. Okay, so yeah, so this is the hierarchy that we can represent using dendrogram. Similarly, you can see that there is another dendrogram in which we assume that, sorry, just a second. Okay, so yeah, so we have this second dendrogram. Here we assume that A and B, they connect first. So A and B connect first. Then here we have E and F that connect first. Then after that, A and B is connected to to C, and E and F is connected to D at this level. Okay, and then we have a final level where these two groups are connected. Okay, so if you cut this dendrogram here, you have two groups. One is ABC and other is DEF. So these are the two groups that are identified by this dendrogram if you cut at this level. Okay, so yeah, so this is the explanation of the dendrograms. So in the dendrograms, you can see that there are three different terms that you need to understand now. Just a second, I'll put my laptop on charging. Okay, so in these dendrograms, there are three terms that you need to understand. Okay, so the first one is the leaf nodes. What are leaf nodes? All the original nodes will be present at the leaves. Okay, so all the original nodes will be present at the leaves, and all the original nodes will form your leaf nodes. Okay, so then next term is the internal nodes. Okay, so now these are not R1, R2, R3, R4. So these are your internal nodes. Okay, so you can see that internal nodes are not actually there. Okay, so these are the virtual nodes, but they show the hierarchy, or they show that how these nodes are being combined at different levels. Okay, so basically the internal nodes are not actually there, but they are virtually present, and they tell you, they explain the hierarchy in the network. Okay, now third important term is least common ancestor. Okay, so now let me explain you what is the least common ancestor. So if I consider A and B, okay, so if I consider A and B, so you can see that A and B has R0, R2, R3, and R4. These are the ancestors for A and B. Okay, so these are the ancestors for A and B, but amongst these, R naught is the most recent one. Okay, so R naught forms the least common ancestor. Okay, so R naught is the point where these two connect. Okay, these two connect first. So that is why we have this term as least common ancestor. Okay, so if this is clear, okay. So
Ma'am, quick question.
yes,
Why is it called least when it's like connected
that,
right away?
yeah, that is just the nomenclature.
Okay,
Least
and
common.
this is nothing but a tree, am I right?
Yes, yes, it's a tree. It's a dendrogram, and if you want to, have more details about that, so you should study agglomerative clustering algorithm. So this is very popular clustering algorithm in data mining. So it properly explain you how the clusters are formed and how this hierarchy is formed. So it's a simple algorithm. It won't make much take your much time. So go through that algorithm and it will explain clearly that how these dendrograms are formed. So it tells you the hierarchy. You can see कि पहले A and B connect हुए, फिर C connect हुआ, फिर D connect हुआ, and so on. Is it clear?
Yeah, yeah, yeah.
Yeah. Okay, so up till now, we have covered these steps. Okay, so first we have seen that we had a network. Okay, and is network made there was some hierarchy. Okay, and that hierarchy is identified using the that hierarchy is identified and we represent it using the dendrograms. And there can be many dendrograms for a particular network. Okay, so now once the dendrogram is identified, we have these internal nodes. Okay, and each of these internal nodes will have a probability. Okay, so there will be certain probability that these internal nodes are formed. Okay, so now let us try to understand how we will calculate this probability that is associated with these internal nodes. Okay, so now this was our original sorry. Okay, so yeah, so this was our original network that we are seeing. Okay, so now in this, in order to calculate the probability, okay, so you need to understand these terms, ER, LR, and RR. Okay, so let us assume that I have this dendrogram A, B, C. Let me check what was the option A, B, C. E, and F. Okay, so now I try to construct the dendrogram for this network A, B, C, D, E, F. Okay, so these are the nodes. First, I have this, this is connected to this is further connected to this, and this is further connected to this. Okay, here I call this node as R0, this is R1, this is R2, this is R3, and this is R4. Okay, so this is the dendrogram for this particular network. Okay, so now I've told you that each internal node will have certain probability associated with it. So how we are going to calculate the probability of these nodes? For that, we need to consider LR and RR. LR is the number of number of nodes in a right leaf, and RR is the number of nodes in the left tree. Okay, so for example, for R naught, how many nodes are there in the left tree? Just one. Okay, and how many are there in the right tree? Just one. So LR and RR value for R naught will be 1 and 1. Okay, so similarly, let us consider this node R2. For R2, what will be the LR value? What will be the LR value?
1.
No, it will be 2. Why 2? Because on left side, I have two nodes. In the left subtree, I have two nodes. Okay, so left LR becomes 2 here. And what will be the RR value for R2?
That will be 1.
That will be 1. Correct. So I hope the definition of LR and RR is clear to you. Okay, so now let us try to understand what is ER. ER is the number of edges in G. Okay, so number of edges in the original graph whose endpoint has R as the least common ancestor in D. Okay, so now let us consider this R2. Okay, so for the LR2, you will see that okay, so you had these two trees. One was in the left, you had AB, and in the right, you have C. Okay, so these two are the different subgroups. Now you want to see that how many edges are there in the original graph that joins these two groups. Okay, so how many edges in G whose endpoints has R as the least common ancestor? Okay, so we can see that there are these two edges. Okay, so there are these two edges that combines A, B, and C, okay, at R2. So ER value will be 2 here. Is the calculation clear for ER value? ER is the total number of edges in your original graph whose endpoint has R as the least common ancestor. Okay, so you can understand it like कि जो R है, internal node है, that is joining the groups, right? So if it is joining the two groups, so like how many are the edges that are actually joining these two groups together? So in this, we have these two edges that are joining these two groups. Is it clear, the calculation of ER? Now let me check for R3. For R3, what will be the ER value? Okay, so for R3, in the left, we have ABC and in the right, we have D. Okay, so in the left, we have ABC, in the right, I have D. And how many edges in the original graph that combines these two groups? That is 1. Okay, so here ER value will be 1. So is this calculation clear to everyone?
Yes.
Yes, ma'am. Yes, ma'am.
Okay. Now, okay, so if I consider R3, okay, so let me consider R3 here. So I had this one group that was ABC and the other group that was D. Okay, so how many total number of possible connection could be there between these two groups? Can anyone tell me? What will be the total possible number of connections between these two groups?
Four.
Okay, so let me explain you. The correct answer is 3. Okay, so how 3? So here in the left subtree, I have 3 nodes, right? So I have 3 nodes here. So my LR value is 3. And in the right side, I have 1 node. Okay, so in the right side I have a 1 node. So if you want to see that how many total possible connections could be there, so either D could combine with A, or it could combine with B, or it would combine with C. Okay, so these were the only 3 possible connections, and those possible connections can be formed by formula LR into RR. Okay, so the formula LR into RR gives you the total possible connections that could be there in these two groups. Okay, so now let me erase this. Okay, so at each node, I told you that there will be certain probability that will be associated with each node, okay, each internal node. And I have told you that it depends on ER, RR, and LR values. Okay, so these are the 3 different values that you need to understand. So yeah, so the probability, okay, so the probability at each internal node, the optimized value will be, okay, so the formula is not given in your slide. Let me write it down. So the probability is ER upon LR into RR. Okay, so this is the formula for your probability at each node. ओके सो ER क्या है? ER तो है जो ओरिजिनल ग्रुप में, जो ओरिजिनल नेटवर्क में एजेस हैं. ओके, एंड योर डिनोमिनेटर इज total number of possible edges. Okay, so this gives you the probability of this internal node. Okay, so yeah, so now let us try to verify the calculations that are given. Okay, so for here, what was the value of LR? Okay, now let us see at R naught. At R naught, my LR value is 1, RR value is also 1, and ER value is also 1. Okay, so how many edges are there that are connecting these two groups? That is 1. Okay, so that is why probability is 1 by 1. Okay, so the probability is 1 here. Okay, so now let's check at R2. At R2, your LR value is 2, right? RR value is 1. And then your ER value. Okay, so how many edges are combining these two groups? That is 2. Okay, so the probability is 2 by 2 into 1, that is 1. Okay, so this is the calculation for R2. So now let us check the calculation here for R3. For R3, what is the LR value? What is the RR value and what is the ER value? Okay, so yeah, what is the LR value?
3.
Correct. What is the RR value?
1.
1. What is the ER value?
Oh, 4 by 3.
No. So it's this group and this group. So how many edges are there in the original graph that are joining these two?
1.
1. Okay. So this forms 1 by 3.
Okay.
Clear?
Yeah.
So let's again check for R4. Okay. So for R4, what is LR value?
4.
Correct. What is RR value?
1. No. Hold on. 2.
Correct. What is ER value? So
Yeah.
now we have this group. Sorry. So I have on right side, I have this group, and on left side, I have this entire group. So how many edges are connecting these two groups?
2.
Yes. So what will be the probability? Probability will be 2 into 2 by 4. So this will be 1 by 4. Okay, so in this way, you can calculate the probability of each internal node. Okay, so yeah, so now try to understand that you have these multiple dendrograms, and for each of these dendrograms, you identify the probability of these internal nodes. Okay, so now what was our original aim when we started this algorithm? Okay, so our original aim was I want to predict the edges. Okay, but how using these probabilities can we predict the edges? Okay, so now let's try to understand that. Now let's try to, okay. So yeah, so let us assume this was the graph that we have, okay, and these are the two dendrograms that we have, okay, and we have calculated probability of each internal node. Now you want to calculate what is the probability score, what is the probability score that ENFH is there, okay, so you want to predict the score for B and F. Okay, so for these two edges, okay, so you have B and F. You have B and F here. Okay, so in this particular case, first of all, you will try to calculate the least common ancestor of these two nodes. So what is the least common ancestor here in D1 for B and F? What is the least common ancestor?
Which one were you asking? Which graph are you asking for?
For D1, let us see this dendrogram.
Hmm.
What is the least common ancestor for B and F?
It's R4.
Correct,
R4.
correct. It's R4. Okay. Similarly, in this dendrogram, what is the least common ancestor?
R4 again?
R4 again. Okay. So what you are going to do is, if you are having these two probabilities, you are going to consider these two probabilities. Okay. And then you are going to find the average of these two probabilities. Okay. So it will be 1 by 4 plus 1 by 9 divided by 2. Okay. So this will be the probability score for BF. Okay, so this is how we calculate the the scores for scores using probabilistic model. So is it clear to everyone? Any doubts up till now?
That's clear.
Okay.
Clear, ma'am.
Okay. So yeah, a small another slide I want to explain you. Uh, it is this one, likelihood one. Okay. So see, for a given graph, I can have maybe 10 dendrograms. Okay, so I have these 10 dendrograms and I want to know that, okay, which two or which three amongst these 10 dendrograms I should consider for my calculations. Okay, so now how will you calculate that which dendrograms are more valid and which are less valid? Okay, so for that you can give just now we have given scores to edges. You can also give scores to the dendrograms. And how you will give the scores to the dendrogram? You will calculate the likelihood of each dendrogram. What is the likelihood of each dendrogram? Likelihood of each dendrogram is, you have all these probabilities, you will multiply all these probabilities together, and whatever value you get, that is your likelihood for that dendrogram. So this is the formula for likelihood. This can also be written as this, that we have already calculated. Okay, so you have to multiply all the probabilities of internal node. That will give you the probability, that will give you the likelihood of that dendrogram. Okay, so maybe based on the likelihood score, you can select some top two or four, and then using those two or four dendrograms, you can calculate the probability of an edge. Okay, how you calculate the probability of edge? Probability of edge is the average of the probabilities that you calculate. Okay. So yeah, so I'll give a quick recap of this algorithm. So in this algorithm, first of all, like we identify the hierarchy in the network. Okay, so once you identify the hierarchy, that hierarchy can be represented by using the dendrograms. Okay, so now for the dendrograms also, you can calculate the likelihoods and you can select whichever the dendrograms you want to consider for further calculations. Okay, so now for these dendrograms, suppose you want to predict that whether there is an edge between a pair of nodes. Okay, so for those pair of nodes, you are going to find the least common ancestor in each of the dendrogram. You are going to identify the probability and you are going to identify the average probability. So the average probability value gives you the score or gives you the probability of that edge to occur. Okay, so now once you have the probabilities of all the unconnected edges, okay, so you're going to consider all the unconnected nodes, all the pair of nodes that are not connected. So you are going to identify all those pairs, and for all those pairs you are going to calculate these probability values, and then what you will do, you are going to sort it based on the highest probability to lowest probability. Then you can either use threshold or you can select the top k edges. Okay, so this is how we do the edge prediction or the link prediction using probabilistic methods. Okay. So now, what is the advantage of or disadvantage of this probabilistic method? So can anyone think what is the advantage or disadvantage of this probabilistic method? What do you think is the advantage or disadvantage as compared to the local method or the global heuristic method that we have studied before?
It is cheaper and faster than others.
Okay. Anything else?
The result may not always be accurate.
Mm-hmm. Okay. Okay. So one advantage that I want you to think is कि उसमें you were getting a score, okay, and इसमें you are getting a probability. So which one do you think is more interpretable, probability or score?
Probability.
Correct. So yeah, so this model is more interpretable. It is easy to interpret. So yeah, so this is one of the major advantage of probabilistic method. So let's quickly, cover the differences between the heuristic method and the probabilistic method. So in the probabilistic method, you used to get score. Here you are getting the probability. Now, uncertainty. Uncertainty is like it's very difficult to predict a score. So you might have like using the heuristic method, you might have the value as maybe like 150 or some other values. So for from one method you have the value 150, from other method you have the value 1000, okay, and so on. So, like, it's very difficult to interpret those values. But on the other hand, if you have the probability, so it gives me a proper interpretation of the data. Okay, ki how much probability is there, how much certainty is there that this edge will be there. So that interpretation becomes easy with the probabilistic model. Okay, so then like even like when you want to predict the variables, okay, so in the heuristic method, you cannot, it depends either on the local, it either depends on the local neighborhood or it depends on the path. Okay, so you cannot really predict the variables. But on the other hand, in probabilistic method, you can, also predict the variable values of the nodes. So if you want, you can research a little bit more on this point, that how using these probabilities you can identify or you can predict the value of the attributes. Okay. So yeah, so interpretability we have already covered, and this is based on heuristic, this is based on statistical method. So these were the differences between the method. So yeah, so with that, we have covered our topic that was a link prediction. So I hope the explanation of link prediction is clear to you all, right? So in the link prediction, we have covered three types of methods. One was local heuristic based, global heuristic based, and probabilistic method. And in each of these, we have covered different algorithms. So I hope the notion of these method is clear, and when to use which method also you got certain idea. So then like whenever like you as data scientist, you want to, predict the links, now you have the intuition that what all are the different methods and like in which situation, which one will be more suitable. Okay, so yeah, also I would like to add that there are like many different algorithms. These were only just the few algorithms that I have covered, but actually like there are a lot of research area, lot of research papers in this domain, and there are a lot of algorithms. Okay, so yeah, so based on your intuition, now you can select the different algorithms for different situations and for different application. Okay, so with that, we will end our topic, that is link prediction. And now we will move on to our next topic, that is information diffusion. Okay, so in today's lecture, we won't be going into the algorithmic details of this topic, but we are going to have a high level discussion on information diffusion. And then in tomorrow's lecture, we are going to cover the algorithms for information diffusion. Okay, so first of all, what is information diffusion? So, anyone want to answer? What do you think is information diffusion in the network?
Spreading of information throughout the network.
Correct, correct. So yeah, so diffusion is the net movement of anything from a region of higher concentration to the region of lower concentration. So yeah, so in the simple words, so how any information spreads in a network. So the study of this particular phenomena is called as information diffusion. Okay, so yeah, so sometimes when you are, for example, advertising, okay, so you want to select some nodes, or you want to select certain people or certain influencers through which your information should spread fast. Okay, so if you have a proper knowledge of information diffusion, okay, so how these algorithms work, what is the science behind it, so if you have a full knowledge of this, then it makes you easy to select those influencers, okay, or those people whom you should reach in order to advertise your product. Okay, so because you need that, if you select these people, then mathematically, if you use the information model, the information will spread really quickly. Okay, so yeah, so that kind of decisions can be taken by studying this topic. On the other hand, like there is another very important problem, that is spreading of disease. Okay, so in the spreading of disease also, like you need to have a proper understanding of how the disease is being spread. Okay, so in information diffusion, basically you have these different type of entities. So the first one is the sender. The sender is the one from where the information spreading starts. Okay, from where the like if you are considering the epidemiology network, from where the spread of disease start. So that particular nodes are called as senders. Or like when you are considering the initial stage, okay, the very initial state when the information spread starts, so that but at that particular state we call these senders as seeds. Okay, so we can also call those senders as seeds. Okay, so you have this product and you maybe reach influencer A1 and A2. Okay, and then they spread the information, those people they further spread. Okay, so then initially, the nodes which started the spread, they can be called as seeds. Okay, otherwise, whoever is sending the information further is called as sender. Okay, then we have the receivers. Receivers are the group of entities who are going to receive the information diffusion from the sender. Okay, and then we will have the medium. The medium is the channel through which the diffusion of information is sent from the sender to the receiver. Okay, so yeah, these are the different advantages of the information diffusion. So first of all, we have healthcare department. Okay, so like in COVID time, we all have seen that we had these vaccinations, and if you remember, at very early stage, okay, at very early stage, they started vaccinating the public sector people. Okay, so they started the vaccination with public sector people, and then there was certain hierarchy. I think then children, and then like later on, it was that it was available for common people. Okay, so why that hierarchy was there? Okay, so why that hierarchy was there? Anybody, can you think? So yeah, so whenever you have limited resources, okay, so whenever you have limited resources and you want to quickly stop the spread of disease, okay, so you will try to identify those people जहाँ से spread maximum हो रहा है. Okay, जहां से spread होने के chances maximum है. Or in the other words, you would try to vaccinate the people whom you want to save. That is another aspect. But you will try to vaccinate those people जहां से like one community to other community. डिजीज स्प्रेड होने के चांसेस ज्यादा है. Okay, so if you consider these public sector people, they are connected to a lot of different people who belong to different communities. Okay, so for example, if I have a person maybe who is an IAS, okay, so he might be meeting different people from different states, or he might be meeting different people who are from different economical backgrounds. So you can see that he can be responsible for spreading this disease to different communities. So if I want to stop the spread of disease from one community to another, so this can be one of the probable choice for stopping the spread of disease. Okay, so this is how the decision was taken, and that is why studying the information diffusion is very important. Yeah, so same is the case with your epidemiology spreading. Then comes your social political cascades. Okay, so now if you want, you have these political parties, okay, and you want their propaganda to be spread fast. So just like I have given you the example of advertisement, you need to choose the right people. You need to choose right people to spread your word. Okay, so similarly, like if you belong to a political party, you need to have proper medium, proper people through which you should spread your propaganda. Okay, so yeah, so if you spread through these proper people or proper influencers, then your propaganda will spread fast. Okay, so then we have financial market cascade. So in the financial market, we have seen many a times that certain stocks, they become more popular. Okay, and certain stocks, like why these stocks become popular, and like how this particular stock, it become viral to everyone. Now everyone knows about it. So that is again an application of your information diffusion. Similarly, in the social networks, okay, so you have this fake news virality. Okay, so there is again a lot of that has been done in this area. The fake news spread, why the fake news, they spread really fast. Okay, and how to stop these fake news spreading. So you should select certain nodes beyond which the information should not spread. Okay, so yeah, so that is your fake news. Then we have belief spreads. Okay. So certain times it happens that sometimes it can happen that certain information is not true, but now everyone believes on that information. Okay. So why this is there? Because of this information diffusion. If certain information that is being repeated again and again, even though it is incorrect, it sometimes like people start believing that it is so yeah, here I would like to give one of the example. So you might have remember, I think there was this pilot who ejected in Pakistan. His name was Abhimanyu, if you remember. So I have a few friends from Air Force. So those people, they told me that Abhimanyu's action was not really appreciated in the Air Force. Okay, why? Because we lost one of our airplane there in Pakistan. They told me that Abhimanyu was not really instructed to enter Pakistan. So now because he entered, we lost the airplane as well. Okay, so but in the news we were shown him as a hero. Okay, so in all the news media we were shown him as a hero. So because the media people, they showed it like this, so that becomes the reality of today. So this is how social network works, and it is very important to understand all these concepts. So yeah, so then there is this another notion of information cascade. Okay, so now let me construct a Twitter network for you. So I have this person. This person is followed by A, B, C, D. Okay. And maybe these people are further followed by a few people. Okay, so let us suppose I have this network. Okay, so now there is some news that this node tweets about. Okay, so this tweet reaches these nodes. Okay, so this becomes sender and these are the receivers. So maybe now B and D, they propagate, they further, tweet this message. So they further tweet the message and this message reach to all the people who are following them. Okay, then maybe we have one of the node here that further tweets it. Okay, so now this becomes, if I consider this particular tree, so this is, then I have a node B here. B is further spreading, and then one of the node here that is again spreading. So if I see this particular graph, this forms a directed acyclic graph. So this directed acyclic graph is information cascade. Okay, so this particular phenomena where we are spreading the information from one node to another in the form of directed acyclic graph, this is called as information cascade. An information cascade is a phenomena in which the number of people make the same decision is a sequential fashion. Okay, so these people are making the decision or they are spreading the information in a sequential fashion. That is called as information cascade. From one person, the information spread to another, and then from another to further on, and so on. Okay, the phenomena is found widely in behavioral economics and networks theory. So this phenomena is widely seen in our social networks, and it is similar to, but not identical to, Hertz behavior. Okay, so I will be explaining you what is Hertz behavior. So before that, let us see this particular graph here. Okay, so this particular graph is showing the adoption of hybrid seed corns by farmers of US. Okay, and here we are seeing the charts that are showing the data from different states. Okay, so we have these different states, Texas and all. So we have these different states, and it is showing like how the hybrid seeds are being adopted by farmers from different states. Okay, so now you can see that there is a difference in the trends in each of this state. So this could be because how these seeds were advertised, because like which influencers you choose, because like how the communities were connected there. Okay, so yeah, so in order again, like why we are studying all these, we are studying all these to motivate ourselves towards this topic, that why identifying important nodes at the first is important, and then why like studying like the spread of the information is important in the social networks. So yeah, so then we have this behavior called as Hertz behavior. Okay, so generally, like let's take an example of Netflix and Amazon Prime. Okay, so now like for example, like if I live in US. Okay, so if in I live in US, and in US we know that most of the people they subscribe to Netflix more as compared to Amazon Prime. So now if I too live in US, so I will also eventually I will opt for Netflix as compared to Amazon Prime. So this is what happens. So we try to follow what all our neighbors are doing. Okay. So on the other hand, if I'm living in India, maybe because of the cost, okay, like Amazon Prime is its subscription is cheaper than the Netflix. So maybe I'll go for, if I have to choose among these two, I'll choose Amazon Prime, because like that has more Bollywood kind of stuff, and Netflix has more of a Hollywood kind of stuff. So yeah, so based on these things, so here the intuition is that based on how our neighbors or where we are, based on how people are behaving around us, we start following that. Okay, we start following the same trends that people around us are following. So this particular behavior is called as Hertz behavior. the behavior of individual in a group acting collectively without centralized direction. This is called as herd's behavior. Human based herd behavior, demonstrating riots, general strikes, regress gatherings. So these are some of the examples of herd behavior, because because your friends are participating in a certain strike, you will also go and maybe you will go and participate in that strike. So this behavior is called as herds behavior, often as a useful trait in marketing. Okay, so this particular property is used in marketing. It is used properly can lead to increase in sale. So if you use this property properly, it can lead to increase of the sales. Okay, so then there is this another concept of echo chambers. Okay, so echo chamber is same only, there is one information, you keep on repeating that information, and eventually that information is accepted by a lot of people. Okay, so this behavior that I have already given you an example. So this behavior is an example, again, an example of of the information diffusion. So yeah, uh, okay. So yeah, with that, I think should I cover a few? Let me cover these few slides as well, so that we are done with the introduction of information diffusion. And then from tomorrow's class, we can straight away start with the algorithms related to information diffusion. So yeah, in this particular slide, you can see the trends of this is epidemic Ebola spread. Okay, so this graph is Ebola spread in maybe different parts of West Africa. Okay, and you can see that how this disease is being spread. So even during the COVID time, you have seen that there were certain spikes. Okay, so there were spikes at different times. So so depending on government strategies, so the government have to take certain decisions. So that can be either certain rules they have to implement. For example, there was this lockdown, or they have to come up with vaccination or some other strategies. Okay, so based on those, you can reduce it. Okay, you can reduce it, or you can stabilize that spread. So yeah, so with that, we will complete our today's lecture. From here onwards, we have the algorithms. So the algorithms we will cover in our next lecture. So up till now, any doubt anyone wants to ask?
I'm good.
Okay. Sure. With that, we will end today's lecture. So thank you, everyone. See you tomorrow for the information diffusion algorithms.
Um,
Thank you.
Thank you, ma'am. Ma'am, one more thing we wanted to discuss with you. It's regarding the assignment. There are two parts of the assignment that have been given to us, and then the second part, it is about information diffusion algorithms,
Yes.
and the due date is today. However, we are
Yes.
going to read about. I mean, we are going to have this session tomorrow.
Yeah, so that's okay. Like you can use the generative AIs. So you can have these days you don't have to implement it step by step, right? So you can take the help of generative AIs, and you can use these functions directly to implement that algorithm. So you don't have to implement the algorithm step by step, but you can use one of the algorithm, any one. That's why I did not specify, you can use any one of the algorithm, although the intuition was shared way before when we were doing the community detection algorithms. So during that time, I have discussed the intuition of information spread briefly. So don't worry about that. You can straight away use the functions for this part.
Ma'am, and one more thing, it's regarding if the 2 more days of extension can be given, because we all are working professionals and we need a little bit more time. And there is some debugging also we are doing right now, and it needs needing a little bit more time, and we have to sit across. I mean, till the time we are executing this and taking out the outputs and all. So if it's possible for you, can you extend it with just by a day or two?
Okay, it is difficult. Okay, sure, I'll do that. I'll do that. I'll extend by 1 day. I'll give you 1 more day for submission.
Thank you,
Okay,
ma'am.
ma'am. Thanks a lot.
Thank
That
you.
helps.
Anything else? Anyone? Sure. With that, we'll end the session. Good night, everyone. Bye.
Thank you, ma'am. Good
Right,
night, ma'am.
ma'am. Thank you.
Bye.